what if in the TLS handshake, instead of giving an X509 certificate signed by some clown that I've never met, have no idea whether they're trustworthy, who, if I look at their certificate, I'm meant to trust that they're never going to tell a lie for the next 15 years. Instead of pushing me into a suspension of disbelief that is woeful, instead of that, why don't I simply say, here's the public key, and here's the DNSSEC proof of why this public key is an intrinsic part of that domain name, which is all TLS is trying to do.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time on Ping, I'm talking to Geoff Huston from APNIC Labs again, in his regular monthly spot. In the second of two parts on the topic, Geoff and I continued the conversation about the state of deployment of DNSSEC compared to other technologies such as TLS. Last time, Geoff left things with a cliffhanger, having pretty comprehensively argued for a failure to launch DNSSEC across 30 years, a very apparent market failure. In this episode, Geoff explores the possible changes to how we use the underlying transport mechanisms for DNS, so we don't throw the baby out with the bathwater deploying DNSSEC. The value proposition in DNSSEC is there if we can make it work at scale and provide a service to TLS anchoring their PKI. So, last episode, we left our hero tied to the rails of the railway line as the steam train comes down the tracks, stuck in the barrel about to go over Niagara Falls, trying to disarm the bomb in Fort Knox before it blows up.
Yeah. Tick-tock, tick-tock.
So, we were talking DNSSEC and TLS, Geoff, weren't we?
Yeah, we were kind of looking at the adoption of technology as the actions of a market rather than by administrative fiat. And by that metric, TLS has 97% of all secured web objects are secured transport layer security, TLS. Yet when we look at recursive resolvers and look at the names that they're trying to resolve, down under 1% of the names that people are actually using are DNSSEC signed, and about only 1/3 of the user base will attempt to validate them.
So you're going very strongly to market failure.
Well, unless you can point someone who's in charge of the DNS, and while I'd love to think that, Vince is in charge, we all do what he says, the harsh reality is no one's in charge. There's no one telling everyone, software developers, network operators, service operators, DNS operators, there's no one telling any of us what we have to do. It's a choice. And what we tend to do is what everyone else does. But if you sort of sharpen that view, why does the market move in a particular direction? The answer is users express a preference. Users find this the best way to meet their needs.
Cost benefit, basic cost benefit. They don't see a benefit and they do see horrific costs. It's complex, it's slow, and it behaves slightly oddly from most of the user's perspective. But on the other side of the table, there is this kind of concern that trust in names is very important. Now, you argued last time very strongly that TLS is kind of the epitome of useful belief in the integrity of your channel and the identity of the end party. But I'm kind of stuck on the idea there is a linkage between why you believe that certificate and the potential to look at a DNSSEC signed name. I see value in the idea, Geoff. It's the implementation that sucks. And so I kind of want to say, could we do better?
Well, that was kind of the cliff-hanging thing. You see, TLS requires, around about 1,600 people who are not altruistic, with the exception maybe of Let's Encrypt, But on the rest of them, they do things for money. And what they do for money is comment on whether they reckon you own a domain name or not.
People, companies, entities, you mean things, 1,600 things.
1,600 folk. And if I can convince any of them to lie, I can create a fake certificate for any domain name, and every browser on the planet will believe it. This is so risky.
We know this has happened in the past. I mean, this is not just a theoretical problem, it's actually been seen.
It's happened in horrendous ways. One nation state did it to basically intercept traffic going across its international border and finding the passwords of Gmail users. You know, they were reading people's mail, and they had a bit of a dissident problem, and probably after reading their mail, they may have had less of a dissident problem. That's not nice.
No.
You know?
So we want this protection. Consequences follow. We need to have trust in both the quality of the exchange over the wire and the integrity of the keys behind TLS protection.
Right. So if this third-party commentary on TLS is its Achilles heel, is its weak point, and DNSSEC, because of its tight binding into the namespace, I put my keys in my zone. And as long as I don't let my zone fly off with the pixies, it's my zone, it's my keys, and if I can protect the DNS, then that's a pretty secure relationship. And so intrinsically, DNSSEC feels better. It does, but its operational problems are a nightmare. Keys are big. It's not that cryptography creates problems that cannot be solved. They create problems that are very difficult to solve. And the issue is, as computers get faster, you need to create harder problems. And typically that just means longer keys. And longer keys you need more space. You need to send more data. Now, the DNS was never built for DNSSEC. It was a bolt-on afterthought. And if you look at the DNS's design, you're left with a few adjectives. Lean, mean, very streamlined. We can do 1 billion DNS operations a second because there's no overheads. There's no TLS session. There's no setting things up. You send off a UDP packet, you get back a UDP packet. Simple, stateless, really fast.
Well, that's maybe the old DNS world, Geoff, but modern DNS has different flavors. That's not the only kind of DNS out there.
Well, the privacy folk said, yes, we need to add encryption to the DNS. Huge amount of cost. But again, let's point to where has the market gone, and secured encrypted DNS, DNS over TLS, DNS over HTTPS, has kind of gone hand in hand with external open DNS resolvers, where you have to transit the great unwashed toxic glows in the dark internet. And maybe encryption is, just standard precautions for wading through the toxic mess. But in theory, your ISP is your safe haven. You're paying them money. They're acting on your behalf. Very few of the ISP resolvers, your ISP, do encryption, because if you trust your ISP, great, you don't need it. And if you don't trust them, go and find another ISP. Encryption won't help your problems there. So parts of the DNS armored up, but a huge amount of the DNS is still the same simple lean, mean UDP.
So if you look at overlay services, and there's that mantra that we all love to say, tunnels are bad, there's the additional quality. If you try to use an overlay service, you are placing your faith in a third party at some distance from you to do the right thing. So we have overlay networks like Apple Private Relay, and Apple Private Relay provides some surety of trust in the integrity of privacy across what you do, including behaviors in the DNS, Geoff. But it is rather a one remove, isn't it?
It's a one remove, and if I just look at the DNS without the overlays of mask or any other kind of if you strip out the VPNs, the masks, the encrypted channels, and just look at the DNS, if you walk away from a DNS resolver close to you and traverse the internet, you've got problems, absolutely. But there's a deeper thing with DNSSEC, which I think is an accident of time. You see, when we first started looking at DNSSEC, and you got to wind the clock back to, oh my God, 1992, how fast were processors then? Well, I think we were using 386s and we were pumping them by hand or something, hand cranked. They weren't very fast.
It was the VAX era, and we talked about VAX as the eponymous 1-MIP machine. It was the machine that first said it would do 1 million instructions a second. So we're up in the thousands and millions of instructions these days. We're quite a bit north of that.
Let's wind back to that period when we're thinking about how to add digital signatures to DNS. And you've kind of got a choice point then and there. And you can either use a standard DNS server, here's an answer, and at the front, you bolt on a signer. And instead of passing your answer out to the big bad internet, you pass it to the signer who kind of wraps it up and says, here's the signature, and sends out the signature. Now, that requires a lot of processing for a large and busy zone, a lot of processing. And if you get 100,000 queries for the same name, then if you don't do it just right, you're going to generate 100,000 signatures that are all the same. And that's just load. That's just unusually inefficient. And so we opted for the other approach that said, assemble the zone, bring it all together, sign it once, and then treat that signed thing, every entry has its own signature, as kind of the new DNS zone, and just serve it and its signatures as if it was an unsigned zone. Just serve it. And so you're reusing most of the technology that made the DNS fast and efficient, and you only do signing once a day and you do it for the entire zone.
So you still have the cache, the radix tree, you still have serve efficiently.
Yeah.
You didn't change the underlying protocol very much, and you added signatures, but you don't have to re-sign. So there's a bit of appropriate for the times, appropriate for the CPU and burdens, but we haven't changed very much else. And I'm starting to worry you're going to say that might be at the root of why what we have now is a bit of a bad fit.
That might be at the root of what we have now as a bit of a bad fit, George. I said it. Because think about the random name attack just for a second. Now, if I ask for a name that is not in the zone, how do you answer it? Because you haven't pre-computed the answer that says this name that you randomly generated a few milliseconds ago does not exist. I'm unable to guess all the possible queries that I can be passed and pre-compute the answer. And so we start the DNS contortion. And the first contortion is that they invented a new record called the NSEC record. And this was denial with security.
So it's what other people may know as authenticated non-existence.
Thank you.
Proving this doesn't exist.
And the way they did that was kind of clever. And it is pre-computable, that you answer with a span. So let's say you have a zone with A dot example and B dot example. Then you compute a record for A that mentions B and says all the labels greater than A and less than B are not in this domain name, in this zone, signed by the zone owner. So if you get asked for AA, AB, AC, or any other name that is lexicographically between A and B, you can send them this pre-computed answer going, you fell into this span, that name isn't there, and the signature is authentic. And so you're kind of signing the gaps. Very clever.
Yeah, but Geoff, wow, that's a phenomenal cost. That means that for every label you have, you're making two things, the thing and the statement between me and my neighbour, here's the other signature. So you've increased the amount of signing, you've doubled it.
I've doubled it. And I've also got to add a few more signed records, and I end up sending 3 keys back with an NSEC answer.
Yeah.
3 keys. And it's kind of, wow, that's a big answer.
So there's a second problem lurking here.
Yes, there is.
I don't particularly care if you can say what are the values in the reverse address space, because we all know that for any given area of numbers, what are the number digits that lie between them that are an address? There's only 255 values in IPv4. So saying, oh, you're not meant to know all the names doesn't really matter. But there are some zones where people say, the way I do business, I don't want you able to enumerate all things in me. And you've just opened the door to using negative answers to know how to enumerate the zone, because you get told the pairs. So you could walk the pairs.
Right. The only names that a zone owner can sell are the names they haven't sold yet, the ones that don't exist. And the domain name business is actually partially a guessing game of you're trying to figure out what names are still available. And it is a guess because you don't know. It's sometimes names might not be delegated.
So you could buy a name that exists. So I could buy IBM, but the thing is, IBM have to want to sell it, and most of the money goes to IBM, whereas new names, all the money goes to the registry.
Right. So selling names that don't exist is part of the business. Now, NSEC gives your entire business away because now I know the names and all the non-existent names in a zone because DNSSEC told me. Oh, the cryptographers say, oh, God, okay, back to the drawing board. Let's use a complicated hashing algorithm that scrambles the letters of the names, scrambles them, and then sorts the scramble and does an NSEC record across the scrambled hash names. Has your brain exploded yet?
Yeah, scrambled eggs.
Yeah, right.
This is complicated. But the benefit of this is what exactly? That I can prove this name doesn't exist, but I don't reveal all of the things that don't exist.
And I can pre-compute the negative answer. So I can take a zone and scramble the names, compute the negative span records of the scramble, pre-compute that, load it up and serve it easily. So it's all just take that zone, sign it, serve it. You go, well, okay, problem solved. Yes. By all estimates, .com has around 100, maybe 150, maybe 200 million names. That's a lot of signing. And while the folk who run it are folk who do run big infrastructure, that's still a lot of work. And large zones are not easily managed in DNSSEC. They're just not. And to compute things like NSEC records, you've actually got to have the zone around you. Now, we went cloud. We went outsourced. We don't manage the DNS in a whole of zone manner anymore. We've reduced a lot of the internet to simple transactions. And, thanks to Moore's law, the amount of compute power available in 2024 compared to, say, 1994, that's 30 years of doubling every 18 months. Go figure. That's a lot of doubling. So, oddly enough, the hardware to do good cryptography on the fly is now affordable. It's now reasonable.
So the pressure to switch to modes of operation that work on the fly would become a lot higher, right? Because it's cheaper and faster and closer to you, the user. You don't want to have giant thumping central computers running over 200 million names every hour to remake this stuff. That's not a good model for me anymore.
Right, I don't need to freeze the zone to compute the signed zone every X hours. I can use a very, very dynamic zone. And because I'm signing on the fly, I can generate signatures for real names. But what about a non-real name, a name that doesn't exist? Well, I don't need an NSEC record and an NSEC3 record. I don't need any of that. And in fact, the IETF is working on a thing they call NX name that says the name you asked for, this name, AB dot whatever, doesn't exist. Signed.
So a generic signed thing that can be signed on the edge, signed on the fly, and is a trustable statement, whatever it was you asked for, I'm telling you with authority, it doesn't exist.
It doesn't exist. I don't have to pre-compute what you asked for. I just tell you back, this is what you asked for, and here's a signature that says this label does not exist. Generate the digital signature on the fly. You now know it's not there. We all know it's not there, but my answer is so much smaller, and the amount of work to get it is so much less. And all I'm doing is I suppose, exploiting the fact that computers are now able to do this kind of cryptography fast enough that as a server of a large zone, I'm winning. I'm getting better.
So that's an incremental improvement to how we do cryptography and DNS. That means large zones don't have to have centrally managed, run by the clock, periodic, complete resign. We can now manage a signed zone better. But that feels like it's targeting an edge problem here about proving things don't exist and about handling large zones on the signing side. Most of the problems of market failure here aren't about the signing side, are they, Geoff? Aren't quite a lot of them about the consuming side?
Well, let's sort of push this a little bit and understand the nature of two problems with DNSSEC that make everybody who's thinking about it nervous. The first is large answers and standard UDP for DNS are not compatible. Now, large answers proliferate with NSEC and NSEC3 records. So removing that removes some of the probability that you're going to have to generate a really large answer. That doesn't work. So by removing that, you kind of go, well, maybe it can fit in UDP. But what if it can't? Oh, no, I have to then do a truncated answer. Here's what you asked for. I'm sorry, the answer's too big to fit in this margin. Try using TCP. 1 round trip time. Signed by me, by the way, but it's truncated, so who cares? Come along with TCP. Sin, Senac, Ac. Hello, what's this name? You've asked in TCP. Let me assemble and sign the answer. Paddle, 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 paddle.
So you have to do all the work again.
Yes.
There's no incremental benefit from being told truncate, re-ask. It's as if you'd never asked in the first place.
Right. You're kind of no better off. So it's not exactly good, right?
Well, there does seem to be a third option out here, Geoff, which is why not ask in UDP?
Well, that's kind of staring at us, isn't it? The thing that's really staring at you is going, oddly enough, in the early days of DNSSEC, one of the more popular implementations, and we know who you are, Mark, decided by default, Mark, that in all queries, they would set the DNSSEC OK bit on by default to encourage the adoption of DNSSEC. And what that meant is that if a zone was signed, whether you're going to validate or not, by having that bit set, you always push through the signatures, even if the name did not exist. So you're kind of asking for trouble, even if you didn't mean to. Even if you knew nothing about DNSSEC, if you set that bit on, you're going to get back larger answers because they're going to have at least one signature. And if the name doesn't exist, even some more. That's bad. Now, what if you said, if you're using UDP, the DNSSEC OK bit is always clear, even if you thought you set it.
Wow.
I will not give you a DNSSEC.
So flip back to saying, if you're in DNSSEC, you're not in UDP. Wow.
You cannot be in UDP. You can only set the DNSSEC OK bit. You can only ask for a signature over a TCP transport.
Simple. Interesting.
It will be no slower than UDP, truncate bit, try again in TCP. It will be faster than that.
By the incremental cost of doing a UDP, being told it's not sufficient and bootstrapping a TCP, you're going to miss 1 round trip minimum, maybe more.
And you just go, what's TCP? If you want DNSSEC, I'm going to give it in TCP because, quite frankly, the time benefit is good. And the server overheads of serving DNSSEC with TCP is certainly there, but Moore's law, memory, processing capability, it's not going to melt the internet. If you want DNSSEC, ask in TCP.
I'm kind of attracted to this solution because it's mechanistically simple. It's a small amount of code change. It probably has a distribution problem. I like this solution, Geoff, but from past conversations, there's another problem lurking in UDP, isn't there?
We haven't finished. There is another problem.
The CDNS0 thing that we've talked about in other episodes of Ping is kind of sitting there as a problem.
Well, no, the issue is, quite frankly, I send you back a signed answer. How do you know it's the right signature? Oh, well, that's a key question, isn't it? Because I could just send you any old bits.
You've got to do the chain validation. There's extra queries you've got to do.
I've got to make a few more questions. And the first question is, hi, person I just asked, what are the DNS keys for this domain? Send me back a signed answer. So you start in UDP, truncate bit, do again in TCP. Well, okay, we're all using TCP now, and we've got session persistence. So I can then piggyback onto that server, send me the keys for this zone, because I want to check. Okay, good. And now I've got another problem. Are those keys valid? I've got to ask the DNS server for the parent zone. And I've got to ask for the DS record.
Turtles all the way down.
Well, and more to the point, I can't reuse the TCP session. It's a new server, new TCP, and I've got to ask and ask and ask and ask.
And the further down the dot levels you are, the more things you have to ask.
A.B.C.D.E.F.G. You will be wallowing in the mud for some time. That's a lot of work. Yes. The deeper you are down and the longer that chain, the more the queries. That is the second part of the nightmare that is DNSSEC.
But TLS has a trick here, doesn't it, Geoff? TLS says, I can give you some help, mate. Have a bag of info that will help you validate what I just said.
TLS uses TCP, so I can send a lot of stuff. And TLS simply assumes one thing. You have a set of trust anchors. You have a set of trust keys. I will send you in the TLS handshake all of the certificates that can be linked together to cause a validation path. So you don't need to ask anyone. You don't need any other external piece of information. You can assemble a validation path and do that against your existing loaded trust anchors. And go, that's a good domain. With DNS, the answer is, well, go figure, because we're the DNS and we're not going to help you.
Well, we could try a bit harder here, Geoff, if we're in TCP.
Let's try a bit harder and let's actually borrow a bit more from TLS. Because you see, part of the problem with TLS is that it doesn't normally load certificate revocation lists into that initial exchange. Has this certificate that you've presented me with been revoked? Oh, good question. I don't know. Well, should I trust this certificate? Well, maybe you should ask the certificate issuer if it's on their revocation list. How do I do that? Or is this natty little protocol called the Online Certificate Status Check, OCSP, Status Certificate Protocol or something. And I can do this myself, but again, that's a round trip time. And interestingly, it's a massive security leak because now I, the end user, I'm telling the certificate issuer of where I'm going to go.
Yeah.
The name of the certificate that I want validated. It's kind of spewing information that we've learned these days is a bad thing. So interestingly, there was a response from the certificate people. Why doesn't the server, when it delivers this data that relies on that certificate, also package up the OCSP answer, which is a signed answer? If you can validate the signature on that OCSP, that certificate's good. You see, once things are signed, you don't care who tells you it. You care if you can validate it, if you can authenticate it. Doesn't matter if you get it from the gutter. Oddly enough, it doesn't even matter if you get it from a potential attacker. If the signature is good, it's authentic.
Well, as long as it hasn't been superseded by something more recent. So you have to start opening timers that would go with this OCSP to say, here's the state of what you should expect to see as being revoked that was done an hour ago. Well, if they've issued a new one in that hour, you aren't going to know, but it still looks valid.
If we take out the TLS, OCS, server-side OCSP, what it's really saying is, here's some material, and here's some more signed material why you can, for yourself, figure out if you want to trust it or not. I hope your clock's good. I hope your time is accurate.
Yeah.
And I hope your trust anchors are up to date. But if all of that's true, you can trust this from the information I've given you in one hit.
Yeah. Within the limits of how long it's valid and if it's been superseded, it's cryptographically provable that nobody at that point had said, don't trust this.
Don't trust it. So let's go back to DNSSEC validation. So I've got, A.B.C. I ask A for its DNS keys. I then ask B for its DS record and its DNS keys. I ask C for its DS record and its DNS keys.
And you had the trust anchor. You had the root already.
I'm at the root. Now, all of those queries, I know in advance. They're never going to change. A.B.C, it's the same set of queries. Anybody on the planet who wants to validate A.B.C will ask those queries.
And if I'm B.C and I know I'm getting queries for A, I know that they're going to need the stuff about me and the stuff about my parent.
What about A? A knows what's going to get asked.
Yeah.
It knows. So why don't I say, and I'm in TCP, don't forget DNSSEC only with TCP. I say, look, here's the answer. Here's the signature of the answer. And here's the collection of answers that I know you're going to have to ask if you're validating. And here's the answers already here for you. I've assembled them all. Aren't I nice? Why don't you thank me?
Thanks, Geoff.
Thank you. RFC 7901, DNSSEC chained responses. This is not a new idea, but it's kind of borrowed from the same model as TLS. If you're worried about the amount of work you're putting on the client, push it back to the server and let the server do the work once. And every time you get asked, you send back the answers. And it's in the server's interest to demonstrate the signatures are good.
So what this does is it gets rid of a serialized chain of query answer delays, and it leaves behind the necessary component of checking things, but you can cache that, which means if you come back to the same name within the lifetime of the cache, you wouldn't pre-compute. So caching in a client or a resolver close to a client, you're not going to incur round trip delays, but you do have a bit of compute cost. But as you said earlier, computers have got very, very fast. The amount of compute energy to do this work is less of a time burden than it used to be.
Look, if my phone can animate my pictures and turn cats into dogs and do all other kinds of miraculous things with its processing unit, a little bit of crypto is hardly going to take more than a millisecond. Let's face it. This world is overflowing with compute capability, and pushing that load over to the client in exchange for time is a win. Time is really expensive. Compute is really cheap. And this whole process simply says, look, I'm just going to send you all of the elements. Here you are, big bundle, TCP, blank, 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 easy. And then you say, I've got to spend a few cycles doing a bunch of crypto. And the answer is, yes, you do. But the amount of cycles you're going to spend is, in terms of machinery at your disposal right there, right now, is trivial.
So that introduces another small potential improvement, because the algorithm we've been talking about people using in this has been the RSA algorithm, which is relatively cheap to perform on the client side, but an expensive sign. If we switched to elliptic curve, we reduce the cost on the sign time, but one of the complaints in the DNS working group is that clients have to do more work, but the signatures are so much shorter. So we could actually make things even tighter if we're prepared to do work on the client to handle ECC, elliptic curve cryptography.
Yeah, and it's in all the libraries. It's not as if clients can't do it. So it's a case of kind of using what we've learned in the past 30-odd years, that you don't have to make everything on demand just in time. You can pre-compute answers. It's easy. And you can serve that with online signers. So you make the signing burden happen on the server side, but then collect all of that material and say, all you need to do, oh client, is run through the crypto chain and prove to yourself you like the answer. Now, this also gives you the last part of why DNSSEC today is kind of why bother. You see, my laptop, my iPhone, my devices do not validate. They don't. It's too expensive. They ask a validating recursive resolver to, yes, I'd really like you to validate the answer, please, and Google all eights. It's a validating resolver. It will validate. And then it says, Geoff, I've done the work for you. Here's the answer in the clear.
Yeah.
But I've said a bit.
To say it's trustable.
It's trustable. You kind of go, yeah, right. Yeah, truly. But what if I had a TCP session with my recursive resolver? Because I'm doing DOT or something, I'm doing privacy. And I say, look, you've got the proof as to why you like it. Send me the proof in the answer. Oh, that'll be so big. It'll be as big as a normal sized web object. Whoopee-doo. It's not big. It's tiny. And you let my awesome supercomputer, otherwise known as my mobile phone, to process the answer. And the answer is, that's a good answer. Now, at that point, you're kind of pushing over the hump of a lot of the acceptance problems with DNSSEC. Oh, it's really hard to pre-compute the zone signatures once a day or some period. Oh, the answers are huge and UDP doesn't like me. Oh, the whole validation thing means users have to be abysmally patient.
So firstly, we've changed the mechanism to permit sign on the edge that can be done. And secondly, we're avoiding the repeat query problems because we're now packaging up the information you need to validate. And thirdly, we're saying don't use UDP, don't use eDNS0 in large UDP packets. It just doesn't work and it causes fragmentation. Use TCP. And lastly, and this is interesting, Geoff, you've just said, stop expecting anyone else to do the hard yards for you and set a magic it's good bit. Do the work.
Do the work. And then we get to, I suppose, the final thing that has actually been the big change in the DNS over the years. People don't roll their own DNS. Or maybe I do, but I'm a dinosaur. They don't. They've outsourced it. You know, if you look at where does your DNS come from, who's authoritative for the names that you actually use? Route 53 is big. Akamai is probably big. Google's probably big. People have outsourced. We can outsource all of this signing stuff because you can take a normal zone and put a signer anywhere. But it's on the path between the client and the server. And oddly enough, I think, with a little bit of thought work, you could outsource signing into someone who does it for a job, for a profession, and doesn't fall over their feet every second day and blast their domain into oblivion, which is the final piece of nervousness about all of this. If I make the slightest mistake, my domain disappears. And the answer is, yep, DNSSEC is unforgiving. What's the answer? Don't make mistakes. But I always make mistakes. Well, hire someone whose job it is not to.
Yeah.
Hire someone who does that for a living.
I think that this goes back to a topic you've danced around in governance and public policy discussions here, Geoff, around centrality and around the nature of ownership and governance of responsibility. But I think you're making a case. People should look very hard at whether the service outcome is better using intermediaries to do things for them. And if it is, questions of how you govern that and the responsibilities and behaviours are a separate problem. Your service level might improve if you made this decision.
Well, the reality is right now that anyone with a web asset, with an online asset that's worth even a couple of cents, has gone off to CDN land. They've gone off to outsourced.
Yeah. So they've already moved.
They've moved. That decision's already been done. Let's take the bit that we're all having angst about, DNSSEC, and handle it the same way.
Yeah.
Hey, sign my name. Okay, fine, done.
So part of this that I like is that it actually mechanistically is a small number of reasonably straightforward things. Change the signing technology in ways that the domain owner and their relationships to get sign on the edge, that's a problem they can deal with in and of themselves. Change to including validating resolvers in the edge device. Well, if iOS updates, Android updates, Windows and Linux update, that kind of comes along for the ride. Change to not use UDP. It's also in the hands of the client, isn't it? The decision which protocol stack, so that resolves cleanly.
No. The server will never give you a DNSSEC signature if you're using UDPs. The server's now colluding.
Turning off the do encrypt, do check part, that's easily done.
Yeah.
Adding the additional data, well, we've actually had a mechanism in DNS to have additional data for a very long time. Adding things into the answer. I asked you for the address. Here's the additional data. We know how to do that.
Yep. You're using TCP, so it's quite easy to stuff it in.
So this mechanistically is only about coming to a decision to behave like this.
Well, there's more, George. There's more, because I pointed out that TLS has a 97% acceptance rate. Everyone uses TLS and nobody uses DNSSEC. The problem is that if you look hard at TLS, you should be nervous because there is a constant babble of folk poking holes at this distributed trust framework and the third-party commentary on keys. And 10 years ago, there was an effort that was called DANE, Domain Keys in the DNS, that tried to take these public-private keys using TLS and pop them into the DNS. DNSSEC signed, of course. And it kind of went nowhere.
It was too complicated. I remember you writing blog articles saying DANE was extremely hard to set up and get working.
I remember setting it up and it was complicated and slow and it had all the problems. I set it up for my own site for a while and then I gave up because every time I went to my own site, I had to wait for 2 minutes. Hang on, I'm doing some crypto here. Go away. Gee, thanks. But what if in the TLS handshake, instead of giving an X509 certificate signed by some clown that I've never met, have no idea whether they're trustworthy, who, if I look at their certificate, I'm meant to trust that they're never going to tell a lie for the next 15 years. Instead of pushing me into a suspension of disbelief that is woeful, instead of that, why don't I simply say, here's the public key, and here's the DNSSEC proof of why this public key is an intrinsic part of that domain name, which is all TLS is trying to do. But instead of using third-party people doing a third-party commentary, you simply go straight to the source. This is the key of this domain. It's in the zone and it's signed by the zone owner, ka-chunk. And you send that as a DNSSEC signed answer in place of the X509 certificate stuff that's in TLS at the moment.
So it's kind of like certificate pinning, the idea of saying you should only believe I am the bank if the company I tell you signed the cert that says I'm the bank. But instead of it being certificate pinning, it's you only believe the TLS exchange across this protocol if the DNSSEC components that I'm telling you check out okay. And we've made DNSSEC one question, one answer. You don't have to do umpty queries over UDP to get this to work.
And I can pre-package it like a certificate. So there's not even a DNS question. Here's the reason why this public key I'm offering you in a TLS handshake is good. Let's move on. You can validate that answer with your KSK, your root zone KSK, a bit like your, 1,600 trust anchors you currently use for TLS, with your single KSK going, that's a good answer, thank you, let's move on.
Yeah.
And you're done.
Now, this has qualities that actually a lot of people would be interested in, because alongside the DNS and the idea of where does trust come from, there's been quite a few people saying, we don't want our DNS queries randomly proliferating through the universe of authorities. So there's been query minimization, and there's been the people in DNS saying, why are we even relying on the roots to do this when I can preload the zone state of what is at the root and not have to check against something out there? And you've just said, why are you even doing DNS queries if I can give you what looks like a DNS answer and you use the same logic you would have done in a resolver, but you don't ask any questions because I told you.
Yeah, I've told you. And you're right, I don't believe you. And the answer is you don't need to. Run your own encryption across what I've told you, and it's your copy of the root, the anchor point, the KSK. That's yours.
Yeah.
If it checks out, it checks out.
So the perfect DNS is the DNS you don't ask.
Well, the privacy benefits are amazing. Now, I'm half in jest here at this point, but I suppose what I'm trying to say is we've been hammering away at the DNS dead horse for 30-odd years. Do DNSSEC, do DNSSEC.
Yeah.
And the market's been saying, well, no.
Yeah.
And the reaction has been to hammer harder.
Yeah.
To go to more meetings, to say how wonderful it is.
Yeah.
And
but Geoff, as you said in the last time we spoke, if insanity is doing the same thing, believing this time it'll be different, this is pretty insane.
That's right. It is incredibly insane. And TLS, it has, I suppose, the problem of incumbency. It's hard to change when you're the incumbent. But changing the nature of the trust bundle using existing software is actually not a very radical change. Here's something that is, when you decode it, an X509 certificate that you've then got to do some crypto on and apply it against your trust anchors. Here's something that looks like a DNS answer. You've got to put your DNS parser across it and check it against, ultimately, the DNS KSK value that you already have.
All you're doing is taking out the bit where you ask the question. You go straight to the code where you test the answer.
Yep, so the code changes. It's minor. I'm not saying let's everybody do it Geoff's way. But what I am saying is, in some ways, there's enough leeway in today's internet to still keep on thinking about ways of doing this better. And in many ways, and I think even the issue with V6, it's not a case of, oh, no one's listening, I'll just repeat my message, because ultimately you'll hear it. No, that's not true. If it's not working, if the market is not listening to you, you do have to repackage what you're saying and understand the strengths and weaknesses of what's out there and what the market really wants. What we want is secure and trustable in our networks, because I can't see you. I don't know if you're genuine or not. Every time I use the internet, it's a gigantic leap of faith. And the more stories about stolen data and badness and so on, the more nervous I am. So the more we can do to actually make this thing more robust, more trustable, is, I think, in the long run, a good thing to do. And while there aren't instant answers, reload your software, reload your TLS to use this, it's not there yet. But it does say there are directions that we can work on. And I think within our reach, within small numbers of, months, if not years, but certainly, it's possible to do this quickly, to actually prototype up systems.
This is a tractable problem space.
Oh, yes.
We could actually look at this and we could do better without having to throw away everything we like about structured names, domain names, and TLS. There's room for improvement.
Yes.
Geoff, that's been fascinating. Thank you for wrapping this one up. Thank you for carrying forward a story that last episode was heading to a very unpleasant place and giving us some hope for the future.
We've survived the fall over Niagara Falls. Yes. Yay. No, it's in some ways, it's a case of thinking of technology as a conversation, not as a product. Nothing is fixed out there. And to understand strengths and weaknesses and view as malleable is, I think, the key to a lot of the thinking we need in today's internet.
Yep, I think you're there.
Thank you, George. Thank you, dear listener, for persisting with us. Hope your brain hasn't exploded on the way, and we'll see you next time.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also, remember the measurement@apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.